In this lecture, we're going to continue our investigation into the auditory system, specifically on how these pressure waves are transmitted into or transduced into bioelectrical signals and how pitch and loudness are conveyed to within different parts of the components that do convey those bioelectrical signals. And when we think about how that is conveyed bioelectrically, we use the term coding. And coding is a term that is used to indicate how the bioelectrical signals are related to the different characteristics of the pressure waves. And so when we think about the sensation arises from those pressure waves and the amplitude of those waves that will eventually be conveyed inside the ear. So when we think about something like pressure amplitude, that's a sensation detected inside the ear. But when it gets to the level of conscious awareness, eh, in other words, our perception, we perceive that as loudness. And that is, the mechanism for this originates in the tympanic membrane. And so the tympanic membrane acts as a drum, if you will, where increased pressure from those air waves will cause an increase in the displacement of the tympanic membrane. And so amplitude modulation is a term that indicates the magnitude of the pressure waves will be captured and conveyed from the tympanic membrane towards the inner part of the ear. And on the left-hand side here we see in yellow, this is an illustration or a representation of a tympanic membrane, and this represents a pressure wave that is coming from the external environment. So this particular pressure wave has a characteristic amplitude, and when it hits the tympanic membrane, it causes that deformation of the membrane, which will then be conveyed to the inner bones of the ear, the inner ossicles. Now, in this situation here we see what looks to be a similar frequency of these pressure waves, yet the amplitude is much greater. And so as these waves will transmit inside the ear and applies a mechanical pressure against the tympanic membrane, that tympanic membrane will displace and reverberate to a greater degree. Now, how that gets conveyed into loudness, um, we begin with the cochlear partition, and we'll see this on the picture here shortly at the very bottom. So the cochlear partition moves further up and down. Moving further up and down is reference to the previous slide with the two different amplitude pressure waves coming in from the external environment. And as the cochlear partition, and I'll put a box around this here at the bottom of the slide shortly, as that moves further up and down, that will cause a greater shear, a frictioning movement, horizontal movement, if you will, of the tectorial membrane. And that's what we see here illustrated in purple. And that across is across the organ of Corti. And so the organ of Corti, remember, that's the fundamental unit inside the ear that is responsible for transducing the pressure wave into bioelectrical signals. So that will cause a greater displacement of the hair cells, and that's something we covered in the previous part for the auditory system, and we'll make reference to it again here in this part 2 unit. And that greater displacement of the hair cells will lead to a greater release of the neurotransmitters. So as we take a look at the picture here at the bottom, here we have our basilar membrane, which is the base of our organ of Corti. We have our tectorial membrane, which will shear back and forth, thereby displacing the hair cells that project up into the tectorial membrane. And we have our cochlear partition. So as those pressure waves are transmitted through the basilar membrane and towards the cochlear partition, that will force an upward and downward displacement proportional to the magnitude as well as the frequency. We're just looking at magnitude here of those pressure waves that will cause the shear of the tectorial membrane back and forth. Now, in terms of the next sensation that we'll touch on here shortly, we begin by focusing on two key elements because these two key elements will explain how the transduction of sound or rather pressure frequency moves through the fundamental units here, or the key organ of hearing, which is the cochlea. So we have our oval window, which is the portion where the sound that reverberates the tympanic membrane results in displacement of the ossicles and transmits that reverberation into the cochlea. And this particular region of this wound up structure is referred to as the apex, and we'll make reference to the apex here in the subsequent video. So the pressure sensation here that is being conveyed relates to the frequency of those pressure waves. On slide number 2, I demonstrated the two different pressure waves in terms of amplitude, but those pressure waves appear to be conveyed with a very similar, if not the same, frequency. But can we consciously perceive different frequencies? And the answer to that is yes, we can. And we perceive that not as loudness, but as pitch. So the cochlear partition will displace in the way that was explained on slide number 3, but it will displace in different locations differently in order to provide a differential perception of the frequencies regarded as pitch. So the high frequency transmission waves will tend to be transmitted close to the oval window. That's the initial entry point of the pressure waves that will eventually be transduced into bioelectrical signals. So close to the oval window near the base of the cochlea, lower frequency waves will be conveyed further away from the oval window. So closer to the apex, the lower frequency waves have a long mechanical transmission that will eventually reach the apex of the cochlea, and those neurons, the hair cells, are naturally tuned at those locations and become sensitive to that transmission. And that's referred to as place code. The coding or the transduction of a mechanical disturbance into a bioelectrical event. That's what we mean by code, and place refers to the location inside the cochlea. The different parts of the cochlea are quote unquote tuned to these different frequencies. So that ends our first video of part 2, and in the subsequent video, we're going to get into a little bit more detail on how the different parts of the cochlea transmit those different frequency waves.